In this video, we'll start talking about mixtures and how to calculate thermodynamic properties of mixtures. So let's take an example that I did countless times when I was in my PhD, and that is the process of making 70% ethanol solution. So we start with pure, or nearly pure for our purposes, ethanol. We use this as a disinfectant around the lab. So anytime we were working with cells, we wanted to sterilize the surface that we were working with. We wanted to make 70% ethanol. Interestingly, very few protocols that I saw ever specified whether this was weight, mole, or volume percent, and they all happen to be a little bit different. In practice, what we did is we estimated on the high side. So if we wanted to make 70% ethanol, oftentimes we'd kind of eyeball it and make greater than 70% ethanol. We thought that that would be a little bit safer. This would be an incorrect way to do it, but this was a way that I thought would be okay when I first started out in the lab. And that is you would take 700 milliliters of ethanol, nearly pure from the bottle of ethanol. So say about 100% ETOH. And you would take 300 milliliters of water from the faucet, pure water. And what would happen if you mix them? A non-chemical engineer might say, well, 700 milliliters plus 300 milliliters has to be 1,000 milliliters of a 70%, which we are looking for, 70% H2O. I'm sorry, 70% ethanol and 30% water solution. Now, what's wrong with this? If you notice in material and energy balances, I never once did a balance on volume. And that is because this is the incorrect answer. If you mix 700 milliliters of water with 300 milliliters of water, you actually get significantly less than 1,000 milliliters. I think it's 915 or so milliliters based on my previous experience when I did this. So what's going on here? If you look at the shape of the ethanol and water molecules, this is ethanol and this is water. You notice that they're kind of similarly shaped, but ever so different. If you can imagine them interacting with each other, ethanol molecules have interactions with other ethanol molecules. So if I add 700 milliliters of ethanol to 300 milliliters of ethanol, then I would get 100 milliliters of pure ethanol. Vice versa for water. But when I mix them together, something about the way these molecules interact enable them to take up less space when mixed. Takes up less space when mixed. And you can think of this as molecules fitting into interstitial areas in between molecules at the microscopic level. So what is the proper way to solve this problem? I would have to do a mass or a mole balance. So a mass balance in this case is easier. I would get rid of this volume of water. I would say that 300 milliliters of water, when you convert it to kilograms, so I would say 1 milliliter is 1 centimeter cubed, so 1 milliliter per 1 gram of water, and that would give me 300 grams of H2O. I would need to look up the density of ethanol. I don't happen to have that offhand, but I would say 700 times density of ethanol equals the grams of ethanol, which means that I'll call this M1 just for sake of argument, which means that my mix stream would be 300 plus whatever M1 was is equal to the mass of my mix stream. And then if I wanted to calculate this back into a volume, I'd have to go on a website that would list the properties of ethanol. Matter of fact, I'm going to do that. I'm going to see if I could find this and pull it up. So I just looked up the density of ethanol, 0.789 grams per centimeter cubed, which when multiplied by 700 gives me 552 grams of ethanol. That means that my combined mix stream, outlet stream, is going to be 552 plus 300 is 852 grams of a mixture. Now, what percentage of that is water and what percentage of that is ethanol? If I want to calculate what my mass fraction of water is, that is my mass of water, 300 divided by 852, which is 35%, 35.2% by mass water, which means that the balance, 64.8%, is ethanol. So if I wanted to calculate what the volume of this mixture is, I'm going to show you a handy website called Engineering Toolbox. And let me see if I could share that. Share. Okay, there we go. What did I say the ethanol weight percent was? 64 point something. Oh, I can't mark this up. 64% is between these two. Interestingly, we also need a temperature. It looks like it's a function of temperature as well. So let's just say 25 C for sake of argument. And then let's say 64%, we'll round that to 65% to make the interpolation easy. 0.87 is going to be, what is the units on this? Density in grams per centimeter cubed. So 0.87 grams per centimeter cubed, interpolating these two boxes. So the calculation here is just taking the mass of the outlet divided by the density, which we looked up from Engineering Toolbox. So just make a note here. Interpolated at 25 C from Engineering Toolbox. And the answer here is 979 centimeters cubed, which is equal to 979 milliliters. So you can see that this answer is not equal to the intuitive answer of 1,000 milliliters. And why is that? I explained before, it's because of the way the molecules interact. But importantly, I want to introduce the property of a excess property. Or you know what, first I want to introduce the concept of an ideal solution. Ideal solutions. And an ideal solution is one that behaves in an intuitive fashion. So we'll say behaves intuitively. In other words, the properties are additive. Another way you could think about it is an ideal solution behaves as if you were just mixing two chemicals with itself. So in other words, if I were mixing benzene and toluene, for instance, benzene is a cyclohexane molecule like this. Toluene is a cyclohexane with a methanol group like that. Those molecular structures look pretty similar with the exception of this bond over here. Or another example that you can take is hexane and heptane. So hexane has 1, 2, 3, 4, 5, 6 carbons, 1, 2, 3, 4, 5, 6, and heptane has one more. So comparing these two molecular structures look about the same. If you were to mix these two things together, it's really not that different from adding hexane to hexane or benzene to benzene because of the way their molecular structures are so similar. So an ideal solution, when I say it behaves intuitively, that means that if you wanted to calculate any thermodynamic property, so say for instance, internal energy, you would say that the internal energy is a function of temperature and pressure, and also you need the composition now. So TP and X1, these are for a binary mixture. So for a binary mixture, you don't need X1 and X2, you only need the mole fraction of one component because the other one is set because they have to add up to 1. So if I say that the mass fraction is 70%, for instance, that means that the other 30% must be the other component. So for an ideal solution, I can say that this is equal to the weighted average of all of the components. So it's equal to X of component I times the internal energy of component I at that temperature and pressure. All right, so an excess property, in contrast, excess property is the difference between that property and the ideal solution. So for an excess property, we'll call it U excess is equal to U of the mixture minus U of the ideal case. So importantly, if the excess property is 0, you get back your ideal solution once again. I just wrote it here for example in terms of internal energy, but this is also good for enthalpy, molar volume, entropy, and Gibbs. So let's calculate the excess molar volume from the example above. So I'll just apply the same equation to the excess, to the volume now. So V excess is equal to V under bar minus V under bar ideal. So we've already calculated what V under bar is. That's the actual volume that it takes up, 979 centimeters cubed. But we don't have the ideal volume, ideal molar volume. So what we have to do now is convert our mass fractions into mole fractions. I'm just going to convert everything over into moles. All right, so we had 552 grams of ethanol. We do this over in the margin. 552 grams of ethanol and 300 grams of water. Okay, so divide each one of these by the molecular weight. I think I didn't look this up. It's 2 carbons, which is 24 grams per mole, plus 16 plus 6, so 46 grams. This is equal to 12 moles, and this one is equal to 16.7 moles. So total moles then is 28.7, and then mole fractions, so X water is equal to 16.7 divided by 28.7, which is 58%, 0.582, which means that ethanol must be 12 divided by 28.7, 41.8. 418. All right, so I'm going to now plug this into the ideal case solution. So in ideal, it's simply the weighted average. So minus 0.418 times the molar volume of ethanol. So I have to look up molar volume of pure ethanol. So I already looked up the density of ethanol. It's just the inverse of the density is the specific volume of ethanol multiplied by the molecular weight now gets me centimeters cubed per mole. So it's 58.3 centimeters cubed or milliliters per mole. So I'll plug that in here, 0.418 times 58.3 minus 0.582, which was our mole fraction of water. And the molar volume of water should be 18 divided by 1. So 18 milliliters per mole, or centimeters cubed per mole. I just noticed a tiny mistake here for V under bar. I don't need the volume, I need the molar volume. So I need to divide this by total moles. So remember, because I had 12 moles over here and 16.7 moles, my total moles is 28.7 moles, not centimeters cubed. So now I've got consistent units. And I can just calculate this now. If I do this calculation, I end up with the excess molar volume, in this case is negative 0.734 centimeters cubed per mole, which means that intuition was somewhat correct, right? It takes up less space when mixed. So I'll also tell you that not all mixtures have a negative excess molar volume. Sometimes the molar volume will be positive. In these cases, it can be useful to look up a plot of excess volume as a function of composition, if one exists. If it's a binary mixture, there's a chance that it exists. So here is an example of one such plot that I took from my other textbook, the Visco and Dahm textbook. This is a plot of molar volume of mixing, which is very subtly different, and I'll talk about that in a second, for 4 different mixtures. So this solid blue line at the top is propanol heptene. So for propanol, it is 3 carbons, and an OH, and 1 heptene is double bond 2, 3, 4, 5, 6, 7. So different shaped molecules. you notice a trend that the weirder the two, or the further off the differences are between the two molecular shapes, the more wonky the graph will look. So for propanol heptene, we've got pretty different looking molecules, and this OH, this alcohol group, is what seems like it messes stuff up. It gives you a relatively large molar volume of mixing. A solid black line is propanol and hexene. Propanol and hexene. So it's the same propanol now, and hexene is the same, but just one less carbon. So 2, 3, 4, 5, 6. All right, so not that much of a difference between the two, but you notice that some compositions now, we've got a negative molar volume of mixing. So it could be positive or negative depending on what the composition is. So that's kind of weird. The one at the bottom is acetone and methanol. That's a highly irregular system. So acetone is a propane with a ketone, and methanol is just CH4. So different shape molecules there. And then the last one, which you can barely notice, is this dashed black line. That one is methanol ethanol. So methanol and ethanol are similar compounds. So methanol is just OH, ethanol is 2 carbons and an OH. And for that system, so you've got similarly sized alcohol molecules, the change of molar volume on mixing is very quite subtle compared to the other ones. All right, I said I was going to define the subtle difference between a mixing property and an excess property. So for a mixing property, this is going to be defined as the difference. This is the difference between the mixture property and the weighted average of the pure component properties. And the weighted average of pure component properties. So for volume, for instance, the mixing property is going to be the same as the excess property. In other words, the molar volume of mixing, so delta mix for V, is equal to V at TP and composition minus X1 V1 minus X2 V2. All right, so that's for volume. And like I said, for volume, mixing property and excess property is the same. Mixing property equals excess property. Okay, so very subtle difference here is that the mixing property is the difference between the mixture property and the weighted average. The excess property is the mixed property minus the ideal solution property. So why the semantics here? Or why do we have to differentiate between these two? Consider the case of entropy. For entropy, the mixing property is not equal to the excess property. That is because when you mix two chemicals, you inherently increase the entropy, right? So if I mix that ethanol water system, even in an ideal case, my entropy is going to increase. It's not just going to be a weighted average. And that is because the property, the mixing, the process itself increases the disorder, to borrow the common explanation for it. That's a spontaneous process, right? I can mix two things, but I can never spontaneously get them to separate themselves, right? So for entropy, there is a difference. And we're going to talk about that in the next video. I think that's going to be good for today. We'll pick up there on Friday.